Hello, I'm Divyashri Vaivy, working as Assistant Professor in the Department of ECE, SJBIT. In this video, I'll be discussing about delta modulation. So, in some applications, the increased bandwidth requirement of PCM, it is a main reason for concern. We discuss an alternative method of digitally representing analog information source. We call that as a delta modulation. So, in delta modulation, an incoming message signal is oversampled. That is a rate which is very much greater than the Nyquist rate, to purposely increase the correlation between adjacent samples of the signal. So, this is done to permit the use of simple quantizing strategy for constructing the encoded signal. In its basic form, delta modulation provides a staircase approximation to the oversampled version of the message signal. The difference between the input and the approximation is quantized into two levels, that is plus or minus delta, it corresponding to positive and negative differences. Thus, if the approximation, you can observe in the diagram, if the approximation falls below the signal at any point of time, it is increased by delta. Delta is increased, the staircase approximation, it is increased by delta. If on the other hand, if the approximation lies below the signal, then it is decreased by delta or diminished by delta, providing that the signal does not change too rapidly from sample to sample. We find that the staircase approximation will remain within this duration, plus or minus delta of the input signal. So, let us denote the message signal m of t and its staircase approximation mq of t. The basic principle of delta, it is formulated in the set of discrete time equations as E of nts is equal to m of nts minus nq of nts minus ts. EQ of nts is delta signum of E of nts. MQ of nts is mq of nts minus ts plus EQ of nts. So, now if you observe the plot here, this is the dotted line is the message signal. If the approximation, if it is lying below the message signal, it is treated as 0. Whenever the approximation is more than the message signal, then it is treated as 1. Observe, that is what is the basic concept we have used in the delta modulation. So, here Ts is the sampling period, E of nts, it is the error signal. It is the error signal representing the difference between the present sample and the present sample of the input and the latest approximation. This is the approximation. This is the present sample and this is the approximation of it. So, MQ of NTS minus TS and EQ of NTS, it is the quantized version of ENTS. So, this is the quantized version. So, the quantizer output EQ of NTS, it is finally coded to produce the desired delta modulation signal. So, here in the diagram it shows how the staircase MQ of t, here the staircase approximation MQ of t follows the variations in the input signal as it has been given in the equation. So, the second thing, it displays the corresponding binary sequence. Is it 0 or is it 1? So, it is apparent that in delta modulation system, the rate of information transmission, it is simply equal to the sampling rate Fs. Fs is equal to 1 over Ts. So, the principal virtue of delta modulation is its simplicity. It may be generated by applying the sampled version of the incoming message signal to a digital encoder that involves a comparator, quantizer and accumulator. It has a comparator, quantizer and a accumulator. Accumulator in turn it has a delay element and a summation. So, details of the modulator is already been explained. The comparator, it computes the difference between its two inputs. What are the two inputs? That is sampled input M of NTS and the quantized input MQ of NTS minus TS. The quantizer, it consists of a hard limiter with an input-output relation, that is a scaled version of the signal function. The quantizer output, it is then applied to an accumulator which produces the result MQ of NTS, that is equal to delta function I is from 1 to n signum of E of I Ts. So, that is nothing but summation I is from 1 to n EQ of I Ts. So, thus at the sampling instant NTS, the accumulator increments the approximation by a step delta in a positive or in a negative direction. It depends on the algebraic sign of the error signal E of NTS. If the input signal M of NTS, if it is greater than the most recent approximation MQ of NTS, then a positive increment plus delta is applied to the approximation. If on the other hand the input signal is smaller, a negative increment minus delta is applied to the approximation. So, in this way the accumulator does the best to track the input samples by one step, that is either plus delta or minus delta at a time. In the receiver, you can see in the second diagram here, this one. The staircase approximation MQ of T, it is constructed by passing the sequence of positive and negative pulses produced at the decoder output through an accumulator in a manner which is very much similar to the transmitter. The out of band quantization noise in the high frequency staircase waveform MQ of T is rejected by passing it through a low pass filter. At the end we have here at the low pass filter with a bandwidth which is equivalent to the original message bandwidth. Delta modulation, it is subjected to two types of quantization errors. One is the slope overload distortion and another one is the granular distortion or granular noise. So, first we will take up what is the cause for slope overload distortion and then we will take up the granular noise. So, in the previous equation, the digital equivalent of integration is nothing but it represents the accumulation of positive and negative increments of magnitude delta. So, denoting the quantization error Q of NTS as MQ of NTS is equal to M of NTS plus Q of NTS. So we observe that the input to the quantizer is E of NTS. Except for the quantization error, the quantizer input is first backward difference of the input signal, which may be viewed as a digital approximation to the derivative of the input signal, or equivalently as the inverse of the digital integration process. If we consider the maximum slope of the original message signal m of t, it is clear that in order for the sequence of samples mq of t to increase as fast as the input sequence m of nts in a region of maximum slope of m of t, we require the condition that delta by ts is greater than or equal to max of dm of t by dt. So, if uh, um, we require this condition to be satisfied, otherwise what happens is we find that the step size delta, it is too small for the staircase approximation mq of t to follow a steep segment of a input wave m of t, with the result that mq of t falls behind m of t, as you can see in this diagram. This condition is the slope overload, and the resulting quantization error, we call this as a slope overload distortion. Note that since the maximum slope of the staircase signal mq of t here, it is fixed by the step size delta, increases or decreases in mq of t tend to occur along the straight line. So, for this reason, a delta modulator using a fixed step size is also referred to as linear delta modulation. In contrast to slope overload distortion, granular noise occurs when the step size delta, it is too large relative to the local slope characteristics of the input waveform m of t, thereby causing the staircase approximation mq of t to hunt around a relatively flat segment of the input waveform. This phenomenon is illustrated here. Granular noise is analogous to the quantization noise in the PCM signal system. We see that there is a need to have a large step size to accommodate a wide dynamic range, whereas a small step size is required for accurate representation of relatively low level signal. It is therefore clear that the choice of the optimum step size that minimizes the mean square value of the quantization error in a linear delta modulator will be the result of a compromise between these two errors, slope overload distortion and granular noise. To improve the performance, we need to make the delta modulator an adaptive one, in the sense that the step size is made to vary in accordance with the input signal. So, this is about the types of error. So, the change what we make is a delta sigma modulation. As we have previously mentioned, the quantizer input in the conventional form of delta may be viewed as an approximation to the derivative of the incoming message signal. This behavior leads to the drawback of delta modulation in that transmission disturbance such as noise results in an accumulative error in the demodulated signal. This drawback can be overcome by integrating the message signal prior to the delta modulation. So, the use of integration is the manner which will be described now with the following beneficial effects. The first thing is the low frequency content of the input signal is pre-emphasized. Second one is correlation between adjacent samples of delta modulator input is increased, which tends to improve overall performance by reducing the variance of the error signal at the quantizer input. Design of the receiver is also simplified. A delta modulation scheme that incorporates integration at the input, we call that as delta sigma modulation. To be more precise, it should be called as sigma delta modulation, because the integration here it is performed before the delta modulation. So, we can use in the any way. So, this is a block diagram which illustrates delta sigma modulation. In this diagram, the message signal m of t, it is defined in its continuous time form, which means that the pulse modulator now it consists of a hard limiter here, which is followed by a multiplier. The later component, it is also fed from the external pulse generator to produce a 1-bit encoded signal. The use of integration at the transmitter input, it clearly requires an inverse signal emphasis, namely the differentiation at the receiver side. So, the need for this differentiation is however eliminated because of its cancellation by integration in the conventional DM receivers. So, the receiver of a delta sigma modulation system consists simply of a low pass filter as it is seen here. Moreover, we note that the integration is basically a linear operation. Accordingly, we may simplify the design of the transmitter by combining the two integrators 1 and 2. 1 and 2 into a single integrator placed after the comparison as shown in this figure. Instead of having two integrators, we can have it an integrator after the comparator. So, it also provides an interesting interpretation of delta sigma modulation as a smoothed version of 1-bit pulse code modulation. The term smoothness referred to the fact that the comparator output is integrated prior to quantization, and then the term 1-bit merely it states that the quantizer consists of a hard limiter with only 2 representation levels. The reason for investigating delta modulation is its reduced bandwidth requirements when compared to the PCM. For telephone applications, a typical PCM may use 8 kHz sampling rate with a 8-bit representation for an overall binary symbol rate of 64 kHz. As we have seen, delta modulation uses 1-bit representation but oversamples the signal. Typical oversampling rates of delta modulation, it will be ranging from 16 to 32 kHz depending on the desired voice quality. So, delta modulation may provide a net bandwidth saving of say around 50 to 75% over PCM at the expense of more complicated implementation. So, these are the other methods. There are other methods of converting the analog sources to a digital representation, say for example differential pulse code modulation, etc. So, this is all about the delta sigma modulation. So, let me summarize what we have discussed in today's video. We started with delta modulation. What do we mean by delta modulation? What are its equations? How the binary sequence is generated and its block diagram, and then types of errors, then delta sigma modulation.
what is the need and what are the advanced versions. So, these things we have discussed in today's video. Thank you so much.